Sorry about the yellow paper. The arrow is not in your screen. The paper I'm using is yellow. Sorry about that. Ran out of white paper. Today we're going to prove the sum formulas for sine and cosine. In this particular proof, we're going to use vectors and rotation of vectors. Recall that every angle can be represented as a point on the unit circle. Here would be 120 degrees. And the cosine of the angle represented by this point is the first coordinate of the point. The sine of the angle represented by this point is the second coordinate of this. Here is what we're going to do. We're going to take a horizontal unit long vector and we're going to rotate it by an angle of beta. And when we're done, we're going to rotate it further by another angle, say angle alpha. And then we're going to figure out the two coordinates of this point. This x here will be cosine of alpha plus beta, and this y will be the sine of alpha plus beta. So that's the plan. We call the positive horizontal unit vector I and the positive vertical unit vector j. So we're going to be able to rotate any vector if we could just figure out what happens when we rotate the unit vectors I and j. So let's start with I. Say we want to rotate this by an angle alpha. We get this vector. Notice while I is only horizontal, the rotated vector loses some horizontal but gains some vertical. We can decompose this vector into a sum of a horizontal and a vertical vector. Now if we rotate it by an angle alpha, then by right triangle trigonometry, recall this is a unit vector, so the hypotenuse here is 1 long. So that means that this vertical side has a length of sine alpha, and this horizontal side has a length of cosine alpha. Therefore, when we rotate I, that's going to be our notation for rotation. So the vector I, when we rotate it by an angle alpha, is going to give us cosine alpha times I, that's this part, and sine alpha times j, that's this part. So now let's figure out what happens to j. When we rotate it by an angle alpha, then we get this vector here, and that vector can be decomposed into a horizontal and a vertical component. Using right triangle trigonometry, again, this horizontal side is sine alpha long and the vertical side is cosine alpha long. Therefore, if we take the unit vector j and we rotate it by an angle alpha, what we get is not sine alpha I, but minus sine alpha I. Notice that this time the vector is pointing to the left, to the negative direction, and plus cosine alpha times j. So using these two formulas, we can rotate anything, because suppose you have a vector v. Now we already know that every vector can be written as a linear combination of I and j. And so what we're going to exploit is the fact that it doesn't matter whether you decompose and then rotate, or rotate and then decompose. So there is some sort of a commutativity going on. In other words, the vector v rotated by alpha is going to be the same as a times I rotated by alpha plus b times j rotated by alpha. So that's what we're going to exploit. Okay, let's get started. So the plan is that we're going to take the unit vector I. First we're going to rotate it by an angle beta, and then we're going to rotate it by an additional angle of alpha, and then we're going to figure out what this vector is. Okay, so first we're going to rotate I by beta. So here is the formula. I rotated by alpha is cosine alpha I plus sine alpha j. Well, instead of alpha we're going to use beta, but it's pretty much I rotated by beta is cosine beta I plus sine beta j. Next up, we're going to rotate I beta. That's the vector I already rotated by beta. We're going to rotate it by alpha. And I was already trying to go for the notation, which is a little weird. It will looks like that. The vector I rotated by beta, further rotated by alpha. So let's see. We're not going to repeat this line. This line is the one we started. So I rotated by beta further rotated by alpha is the same as cosine beta times I rotated by alpha plus sine beta times j rotated by alpha, like so. So instead of rotating and decomposing, we're going to decompose and then rotate. And just we're going to rotate these components, which we know already how they behave when we rotate them. It's still here. Okay. So I just copied these two rules because the other ones didn't fit. So this thing, I rotated by beta and then by alpha, is the same as cosine beta times the vector I rotated by alpha. That's right here. So cosine beta is getting multiplied by cosine alpha I plus sine alpha j plus sine beta times the vector j rotated by alpha, which is here, which is minus sine alpha I plus cosine alpha j. So notice that we have basically completed the rotation because this is just a vector expressed in terms of I and j. We just have to distribute products and combine like terms to see how many I and how many j do we have. So let's see how many I. So there is an I part here and there is an I part here. I will have the following coefficients: cosine beta times cosine alpha, and from the second piece we're going to have minus sine beta sine alpha. That's how many I. And now for the vertical component, we have cosine beta sine alpha from the first term, cosine beta sine alpha, and from the second piece we have sine beta times cosine alpha, and that's how many j we have. So what do we have? If we have a vector, say I, and we rotate it by beta and then by alpha, that is the same as rotating it by alpha plus beta. And what we got is that, and I'm going to switch terms in additions or multiplications so that alpha comes always first. So we have cosine alpha cosine beta minus sine alpha sine beta many I plus sine alpha cosine beta plus cosine alpha sine beta j. This result means that if we rotate I by alpha plus beta, we get this vector cosine alpha cosine beta minus sine alpha sine beta many I, and sine alpha cosine beta plus cosine alpha sine beta many j. Well, that also means that cosine alpha cosine beta minus sine alpha sine beta is the first coordinate of this point, which is on the unit circle, right? And the second coordinate of this point is sine alpha cosine beta plus cosine alpha sine beta. Therefore, cosine of alpha plus beta is the coefficient of I after rotation. So it's cosine alpha cosine beta minus sine alpha sine beta. Cosine alpha cosine beta minus sine alpha sine beta. And the second coordinate of that point is going to be the sine of the same angle. Sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. And these are what we call the sum formulas for sine and cosine. A few comments. If you look at both formulas have all four of cosine alpha, cosine beta, sine beta exactly one time. So it's sort of just rotating cosine alpha, cosine beta, and sine alpha, sine beta. Both formulas are a sum or a difference of two products, and it's quite symmetrical, and every product has something of alpha, something times beta. And I belong to that large school where we organize these things, we usually organize by the angle. So something alpha, something beta. And my recommendation is that you memorize these two formulas in this form. This is not a derivation that you want to do every time you want to remember these formulas. So you can do it when push comes to shove, but just memorize these two formulas. My other comment is that when we rotated I and j, we basically assumed that our angles are small, say acute, which means smaller than 90 degrees. But the computation and the proof works even if alpha is larger. If it's a rotational angle that's say 120 or 200 degrees, it will always yield for the same computation.